Hello everybody, welcome to Chapter 5.4 Part 1, Fibonacci's Numbers and the Golden Ratio. Fibonacci Sequence. And this is the Fibonacci sequence. It's a series of numbers starting from 0, where every number is the sum of two numbers preceding it. So here is the Fibonacci sequence, and it was named after Fibonacci, an Italian mathematician. In the year 1202, it was first introduced to the Western world in the book Liber ABC. And this is the mathematical formula for it, and we're going to go more into some of these other things. Now, Fibonacci was extremely well traveled, and he traveled throughout the Middle East and elsewhere. He strongly recommended that Europeans adopt the Indo-Arabic system of numerals, including the use of the symbol 0 or Zephyrium. The sequence first appears as a recreational math problem about the growth in population of rabbits in Book 3 of his famous work, just mentioned, Liber ABC, the book of the calculator. The Fibonacci sequence. A famous problem. A man put a pair of rabbits in a cage. During the first month, the rabbits produced no offspring, but each month thereafter produced one new pair of rabbits. If each new pair thus reproduces in the same manner, how many pairs of rabbits will there be at the end of 1 year? The solution to the problem leads to the Fibonacci sequence. Here are the first 13 terms of the sequence, 1 year of rabbits. So you have 1, 1, 2, 3, 5, 8, 13, 21, 34, 55, 89, 144, 233. So let's look at this pattern on the whiteboard. If you notice the pattern, after the first two terms, both are 1. Okay, and if we add those first two terms, we get the next one. So we get 2. Okay, and so that becomes the next number. And then if we take these two terms and we add them together, we get 3, and that's our next number. And then if we add these two together, we get 5, and that's our next number. And if we add 3 plus 5, we get 8, and that's our next number. And then if we add 5 plus 8, that's going to be 13, our next number, and so on, and so on. So that is how, so what it means is each term is obtained by adding the two previous terms. Based on what we saw on the whiteboard, we found that after the first two terms, both 1, each term is obtained by adding the two previous terms. Now, Fibonacci sequences are found a lot in nature. So, for example, irises have 3 petals, buttercups have 5 petals, clematis have 8 petals, black-eyed Susans have 13 petals, chicory has 21 petals, daisies have 34 petals, and dandelions, well, I'm just guessing 55 petals. And as you see, these are all numbers that occur in Fibonacci's sequence. Now, as mentioned a little bit earlier, there is a thing called a Fibonacci formula, and it is a recursive formula. So let us go over to the whiteboard and discuss what a recursive formula is for the Fibonacci sequence. The Fibonacci number is what's called a recursive formula. So what that means is that, remember, we have, let's say we look back at our sequence. And I'll just do the first two. We look at our sequence, 1, 1, 2, 3, 5, 8, 13, 21. We look at etc. and we look at our Fibonacci sequence, and we call F1 1. So this one is F1 is equal to 1 for Fibonacci 1. F2 is equal to 1. And if we want to generalize any of these for any Fn, is equal to Fn minus 1 plus minus 2, minus 2, and Fn minus 1. So for any n greater than or equal to 3. So for example, if I put 3 here, okay, so for example, I'll just put Fn, F3. So that will be 3 minus 2 is 1. So that'll be 1. And then plus, okay, Fn. So that'll be 3 minus 1, which will be F2, plus 2. So that will be F3. So that will give us 2, just like we see there. So we can do that with any of the Fibonacci numbers. So what we just did on the whiteboard was we showed that if Fn represents the Fibonacci number in the nth position of the sequence, then if we have F1 is equal to 1 for the first Fibonacci number, F2 is equal to 1 for the second Fibonacci number, then we can generalize any F sub n equal to F sub n minus 2 plus F sub n minus 1 for n greater than or equal to 3. That means if we plug any n in here, we can find what the Fibonacci number is just by using this recursive formula like I did on the whiteboard. In addition, the numbers of spirals in the middle of sunflowers, pine cones, artichokes, pineapples, to name a few, tend to be Fibonacci numbers. And this brings us to the golden ratio and the Fibonacci spiral. You can create a Fibonacci spiral using sequences that are the size of Fibonacci numbers. So let us go over to the whiteboard and show how we could do this. Now that we talked about the Fibonacci sequence, now we're going to talk about what's called a Fibonacci spiral. And we're going to construct a Fibonacci spiral with the understanding that we have now of a Fibonacci sequence. So let's say we start off with our first 2 units. We take a piece of graph paper and put 2 unit boxes. And 1 plus 1, well, that will give us 2. So what I'm going to do is I'm going to extend here 2 by 2. So there's my 2. And then I continue. I look at this and I'm going to do 2 plus 1 gives me 3. And then I'm going to drop down to here. And I'm going to have 2, 3. This is 5. And then, of course, 8. And here's my 8, the next number in my sequence. 8. And then I have 8, 10, 13. So here I have 13. So now what I'm going to do is I'm going to start over here and I'm going to go around here like this, and this, and this, and here, and then end up back at 1. And this forms what's called a Fibonacci spiral. And as you see, it's a spiral. And if you look at nature, and let me write this, it's a Fibonacci F-I. Fibonacci spiral. Reviewing what we just did on the whiteboard, we showed that we can create a Fibonacci spiral using squares that are the size of Fibonacci's numbers, as mentioned earlier. So using a piece of graph paper, one can construct this spiral just by connecting these the way that I did it on the whiteboard, and you find that you can make what's called a Fibonacci spiral, which occurs a lot in nature, for example, with the Nautilus shell. Thank you very much. I hope that you enjoyed this video. Be well, take care, and goodbye for now.